Okay, so starting out fairly simple. Example 12, we've got an integral here and we've got two different substitutions to have a go at. This is one of these examples where there's more than one strategy that will make life easier and make it quite straightforward to integrate. And which one you choose is either dependent on the question or a matter of kind of preference or what your intuition tells you. So for A, we have that u equals 2x plus 5. Remember, we also will need to replace the dx. So we need to also know what du by dx is. Well, that's just 2. And actually that tells us that we can say dx is a half of du. And we now have enough information to replace every instance of x in this integral. This is really simple. The 2x plus 5 just becomes a u. The dx we've got is just half du. The x is going to take a little bit more work, so I could do with just pointing out that x is going to be u take away 5 divided by 2, because we need to replace the x as well. Every single example of an x needs to vanish. And what that means is our integral of x root 2x plus 5 dx is going to be the same as our integral of u minus 5 over 2 multiplied by root u multiplied by half du. This could do with just a little bit of tidying up. So I'm going to just bring the root u up to the top here. So I've got u root u minus 5 root u over 4 du. And I could reorganize this slightly more. In fact, I'm going to, because it's going to be easier to integrate this if we rewrite this in kind of polynomial form with powers. So this is the integral of u of 1/4 of u to the power of 3 over 2 minus 5 u to the half du. And the quarter we can just pull outside of our integral entirely. It doesn't make a lot of difference at this point in time. So this is going to give us 1/4 of, and then to integrate u to the power 3 over 2, I raise the power, divide by the new power. So that's going to be u to the 5 over 2 divided by 5 over 2 minus 5u to the 3 over 2 divided by 3 over 2. Okay, oh, and then I need a plus c here as well. Now at this point it would be nicer, I think, if we tidied this up slightly. Dividing by 5 over 2 is the same as dividing by 5 and multiplying by 2. And I've also got this 4 here. So this is going to end up being 2u to the 5 over 2 over 20. And the second one is going to end up being 10u to the 3 over 2 over 12 plus c. Oh, look, factors of 2 in everything, so we can tidy this up slightly more. So u to the 5 over 2 over 10 minus 5u to the 3 over 2 over 6 plus c. And I don't really need to do any more than that. That's as neat as it needs to be. And this is perfectly fine. I could rewrite this using surds instead of powers if I wanted to, but it's just not that necessary. We're at a sensible, fairly tidy polynomial. I could also join these terms together into a single fraction and so on and so forth. There's plenty of ways I could reorganize that depending on what I wanted to do with it. But that substitution has made life fairly straightforward. What I do really want to do, though, is remember that u is equal to, right back at the start, 2x plus 5. So I want to re-put this into here. So I'm going to have 2x plus 5 to the power 5 over 2 on top of 10 minus 5 lots of 2x plus 5 to the power 3 over 2 over 6 plus c. And now I'm completely done because I've converted back to in terms of x and my integration is complete. It's a little bit fiddly. It takes some practice and some getting used to, but the integration step we made really neat. It was just a polynomial. Okay, so having sorted that out now one way with our first substitution, u equals 2x plus 5, we can now do the whole process again, but this time we're going to use u squared equals 2x plus 5, and we'll see whether that's more efficient or not, and whether or not we end up in the same place at the end of the process. So if we know that u squared equals 2x plus 5, it's useful to note therefore that u is equal to the square root of 2x plus 5, and actually we might write that later on as 2x plus 5 to the half, because index notation is often more convenient, so that's helpful. We also need to deal with our dx. Now this is going to be tricky, so I can't really deal with differentiating u equals root 2x plus 5 easily. I mean, I can. We can do it with a bit of fiddling around with chain rule and things, but it's actually a bit of a pain to do that. Now, you've got two strategies you could use here. One is you could use implicit differentiation and just differentiate it as is, but another way to think about this is to realize that actually I don't need du by dx. I either need du by dx or dx by du, because if I have either of them, then I have the chance to substitute my dx. So let's just quickly rearrange this to say x equals u squared minus 5 over 2, and now dx by du is actually quite straightforward. The minus 5 over 2 is a constant, it's going to disappear. U squared over 2 is going to differentiate down to 2u over 2. Oh, that's just u. And that gives us that dx equals u du. So now I think I have all the tools I need, because I know what root 2x plus 5 is, that's just here. I know what x is, that's just here. And now I know what dx is, that's just here. So my new integration is going to be, instead of x, I'm going to write u squared minus 5 over 2. Instead of root 2x plus 5, I'm going to write u. And instead of dx, I'm going to write u du. We could do with a little bit of tidying up here. So I've got a u squared out here. So I just need to expand those brackets, multiply everything by u squared. So this is going to be the integral of u to the power 4 over 2. I'm actually going to separate these two terms out now because it will make the integrating more straightforward. Minus 5u squared over 2 du. And hopefully we can see now that this is just integrating polynomials. It's really straightforward. So what we end up with is u to the 5 over 2, not over 2, got to divide it by 5 as well, over 10, minus 5u cubed over 6, plus some constant. We've got this 10 and 6 in the denominator. It always looks pretty familiar, but we need to remember that u is 2x plus 5 to the half. So when I'm replacing the u, I replace it with 2x plus 5 to the half. So I'm going to end up with 2x plus 5 to the 5 over 2, because we multiply when we do a power to a power, over 10, minus 5 lots of 2x plus 5 to the 3 over 2, over 6, plus some constant. And this is exactly the same result we got from the first substitution. It looks exactly the same. So we've got two different alternatives, and it's up to you which one really is easier. I think to some extent the second one is a little easier to tackle, because I don't have any of the fractional indices until the very end of the process. but they were all they're fairly similar in scope.